Okay guys, in this video we are going to talk about free energy. So this is going to be a new state function for us to use. And we'll talk about the relationship between the Gibbs free energy and spontaneity. We'll learn how to calculate free energy changes for chemical reactions, and we'll discuss how temperature affects the spontaneity of a chemical reaction. We'll save this last part for a second video. So in this slide, we're introducing the definition, the formal definition of the Gibbs free energy. And the reason why we do this is because it is related to spontaneity under conditions of constant temperature and pressure. If you'll recall from the last video, we talked about spontaneity in terms of entropy. And in that case, you need to calculate both the entropy of the system and the entropy of the surroundings so that you're looking at the total entropy change before you can judge whether or not a process will be spontaneous or non-spontaneous. It would be convenient if we had a system-only criterion for judging spontaneity, and that's exactly what the Gibbs free energy does for conditions of constant temperature and pressure. Here is the formal thermodynamic definition of the Gibbs free energy. It's the enthalpy minus the temperature times the entropy. Okay, so if you knew all of these values, you could calculate the Gibbs energy of your system. The Gibbs energy is an extensive thermodynamic quantity, so it depends upon the size of the system. The larger your system, the larger the Gibbs energy, and it's measured in units of joules, or more commonly, kilojoules. Under conditions of constant temperature, a change in the Gibbs energy is equal to a change in the enthalpy minus the temperature times the change in the entropy. Now, we've previously learned how to calculate delta H in the review, and we've just learned in the last video how to calculate delta S for chemical reactions, and so it's really not that hard to calculate the delta G for a chemical reaction. Here's how we use delta G as a criterion for spontaneity. If the delta G value is negative, then the process will be spontaneous for constant temperature and constant pressure conditions. If delta G is positive, then it's a non-spontaneous process. In order to apply this criterion, we'll be calculating the Gibbs energy of reaction under standard state conditions, constant temperature and pressure. And what you look at is both the sign and the value of the Gibbs energy change. When the Gibbs energy change is a large negative value, that means the reaction is spontaneous, and at equilibrium we expect mostly products, if not all products. However, when delta G is a large positive number, that means that the reaction is non-spontaneous under standard state conditions, and we would expect almost no products to be present at equilibrium. The third case, if delta G is a moderate number, say between minus 10 kilojoules and plus 10 kilojoules, then we have a true reversible reaction on our hands, and we would expect significant quantities of both reactants and products to be present at equilibrium. Another interpretation of the Gibbs free energy is that it represents either the maximum or minimum amount of work required for a given chemical reaction. In the case of a spontaneous chemical reaction, one that occurs on its own, the value of delta G represents the maximum amount of work that can be generated from the chemical reaction. We call this free energy in the sense that the energy generated by the reaction is used to do work. Here's some examples. Combustion reactions, for example, are used to drive engines in automobiles and other vehicles. Electrochemical reactions are used to power the batteries in our electronic devices. In our bodies, biochemical reactions are used to power our muscles in order to do all sorts of different work. And so the maximum amount of work that can be generated in these different types of reactions can be estimated by calculating the delta G value. We should note, however, that the actual work that can be generated is always less than this value, and so in this sense, delta G is an upper limit to how much work that can be done using a chemical reaction. If you're considering a non-spontaneous reaction, one that won't occur on its own, delta G represents the minimum amount of work required to make that reaction occur. And the actual value of work will always be larger than that delta G value. This slide illustrates how to calculate delta G. There's two different methods. One I've already mentioned. First, you calculate the enthalpy change for a reaction. You calculate its entropy change, and then you combine those values to calculate the delta G value. In another method, we use the products minus reactants approach, where you first add up the Gibbs energy of formation for every product multiplied by their stoichiometric coefficients, and subtract from that the Gibbs energy of formation for each reactant multiplied by its stoichiometric coefficients. And so these Gibbs energies of formation can be found in thermodynamic tables. They're very similar to the enthalpies of formation that we've talked about during the thermodynamics review. And so you use them in exactly the same way to calculate the delta G for a reaction. Here's an example. We are looking at the decomposition of mercury 2 oxide to liquid mercury and oxygen gas. And in part A, they want us to use the Gibbs energies of formation to calculate the delta G value. And in part B, they want us to first calculate delta H and then delta S and then calculate delta G. So for this calculating delta G using the formation Gibbs energies, you take the Gibbs energy of formation for the products, so the delta G of formation for mercury liquid, plus 1/2 the Gibbs energy of formation for oxygen gas, and subtract from that the Gibbs energy of formation for the mercury 2 oxide. So you go to your thermodynamic table and look up these numbers. I've got them listed here. We'll note that the Gibbs energies of formation for elements in their reference forms are 0, just like they are for the enthalpies of formation. So we'll have 0 plus 1/2 times 0 minus the Gibbs energy of formation for the mercury 2 oxide right there. And so we'll wind up in this case with plus 58.43 kilojoules per mole. This indicates that the reaction is non-spontaneous under standard state conditions. In the second part, B, they want us to first calculate delta H using the methods that we've already talked about, and delta S using the methods that we've already talked about in the last video. You calculate those, and then you plug in the delta H and the delta S values here, along with the temperature, which we'll take to be 298 Kelvin in this example, and we get a value of 58.6 kilojoules per mole. And we'll see that they are pretty close to one another. So those numbers should agree fairly well when you use these two different methods. Here in this example, it's the same problem, so I've left it as an exercise for you to try. So you've got the delta H values and the absolute entropy values, and then you've got the Gibbs energy of formation. So you would use this column to calculate delta G using the products minus reactants approach, and then you would use this column to calculate delta H, this column to calculate delta S, and then you would combine those values using this equation here. One thing that I wanted to point out was that delta H values are given in units of kilojoules per mole, whereas S values are given in units of joules per mole per Kelvin. And so there is a unit mismatch between delta H and delta S. And so you need to convert typically the S values to kilojoules per mole Kelvin when you combine them in this equation. So watch out for that unit conversion there. Here's a couple more examples for you to try. I'll leave those as exercises. In this slide, we're going to be talking about the temperature dependence of spontaneity. And so the Gibbs energy of reaction depends upon temperature through the entropy term. And so since delta G is our criterion for spontaneity, we can also control spontaneity by controlling the temperature. And so using this equation here, what I've outlined are 4 distinct cases. Okay, and so in case 1, we're going to look at an exothermic reaction, delta H is negative, that produces entropy, so delta S is positive. And what we're going to do is look at the sign of delta G. So we've got a negative delta H minus temperature, which is always positive, times a positive delta S. And if you have negative minus a positive, you're always going to get a negative number, which means that under these conditions, exothermic and producing entropy, we always have a negative delta G. Such a reaction would always be spontaneous. In case 2, we're considering the opposite. We have a reaction that is endothermic, so it's energetically uphill, and then we have a reaction that produces entropy, so the entropy change, a reaction that consumes entropy, so the entropy change is negative. So we have a positive sign minus a negative sign. That is always going to be positive, and so for this case, delta G will always be positive, which means that the reaction will never be spontaneous. Case 3 and 4 are a little bit more interesting. Here we're going to find some competition between delta H and delta S. First, we're looking at an endothermic reaction that produces entropy. So it's energetically uphill, but entropy is created. And so we have plus minus a plus. The sign of delta G is going to depend upon the value of the temperature. Right? So the endothermic reaction tends to make the reaction non-spontaneous. However, the production of entropy tends to make the reaction spontaneous. And so the question is, which of these two terms is going to win? It depends upon the value of temperature. If temperature is very large, then the entropy term is going to win, and the delta G value will be negative. And so in this case, the reaction will be spontaneous at high temperatures. However, if temperature is very low, so a small value of T, means that the enthalpy term is going to win, and delta G will be positive. And so at low temperatures, the reaction would be non-spontaneous. Case 4 is the opposite. We have an exothermic reaction, which leads to a negative delta G, but then we have a reaction that consumes entropy. So with a negative delta S, we've got minus a minus, and so this could be plus or minus depending on the value of T. In this case, it's the opposite of what we had before. At low temperatures, the enthalpy term is going to win, and we're going to have a negative delta G. But at high temperatures, the entropy term is going to win, and delta G will be positive. So for this case, the reactions will be spontaneous at low temperatures. Here we have some examples where we need to apply that criterion. And so we're being asked to discuss the spontaneity of these reactions in terms of delta G. And so here we have an incomplete combustion reaction. Okay, combustion reactions are exothermic, so this reaction is going to have a negative delta H value. But if we count up the number of moles of gas, we see that we've got 1 mole of gas on the reactants and 2 moles of gas on the product. So this reaction creates entropy. Which situation are we in? Okay, we've got an exothermic reaction that produces entropy. We find that the Gibbs energy will always be negative no matter what the value of temperature. And so we would say that this reaction is always spontaneous regardless of the temperature. In this second reaction, we've got the combustion of iron. And so in this case, the reaction would be exothermic. However, we see that we are decreasing the number of moles of gas, right? We go from 3 moles of gas to 0 moles of gas. So this reaction is going to consume entropy. So we're in the situation where we are exothermic. However, the delta S value is negative. And so here, these types of reactions are only spontaneous at low temperatures. whereas at high temperatures it would be non-spontaneous. What you need to be able to do is to consider various chemical reactions like these, and then be able to deduce what would be the sign of delta G. Is it going to be negative always, positive always, or will it be negative at high temperatures or negative at low temperatures? In this example, we are looking at a phase transition. We're going from liquid water to water vapor, and we're being asked to estimate the temperature at which the two phases are at equilibrium. And so here is the delta G expression, and what I wanted to point out is that at equilibrium, delta G will equal 0. Okay, so when delta G is negative, the forward direction is spontaneous. When delta G is positive, the reverse direction is spontaneous. Equilibrium occurs when delta G equals 0. So using this relationship, we can calculate delta H, calculate delta S, and then by setting delta G equal to 0, we can solve for the temperature at which the two phases are in equilibrium. And so rearranging this second expression gives us temperature equals delta H over delta S. Calculating delta H from the tables, calculating delta S from the tables, and plugging them in allows us to estimate the boiling point. And we see that, of course, the result is not perfect, right? Water boils at 100 degrees Celsius, which would be 373 Kelvin. Here we're off by a few degrees Kelvin, but as I said before, it's just an estimate. Here's another example like that one for you guys to try. And I think I'm going to go ahead and stop this video right here.